Hello, everyone. I'm Fabio Vacchini. As Rafael, I'm a postdoc at the University of Liverpool. And as you can see from the slides, the topic is processing and verification of information streams. So next slide, please. Yeah, so a bit of context. The title doesn't mention them, but we are still talking about agents. And the scenario I want you to think of is basically what is depicted here in the picture. We have one agent that is the one called A in this picture. And then we have a bunch of sensors or components or whatever that provides information to this agent. And the problem is that this sensor will provide a lot of information, and not all this information is useful for the agent. And what the agent does is to check what information is coming and check whether properties are true or not based on the information that it's receiving. So in the particular example, for example, we have S1 is giving some numbers and the agent doesn't want these numbers to be above 20. And sensor 3 is giving some percentages and the agent realizes that there is some weird drop from 49 to 32 and perhaps he has to do something. Now, the next one, Helen. Now, not too fast. There was one in between. Yeah. So if I go back to what the title says, the information streams we are interested in are basically these messages, this flow of messages coming from the sensors to the agent. And the processing and verification we are interested in is more or less what is written in this reddish box from the agent. So checking what values are coming and realize whether or not they satisfy some property and take action based on whether these properties are true or false. Okay, next one. So the general aim of this talk is to introduce some formal framework to deal with this processing and verification of the information streams. The idea is to have, at the end of the day, something that is modular structure, something that allows us to specify the components, so a specific background knowledge, something that allows us to simplify the specification of high-level properties that Rafael mentioned are going to be used by the agent. The framework should allow us, at the end of the day, to have some automation of sanity checks on the specifications. And what is important, we want to delegate the processing and verification part from the agents to some middle layer that is in between the sensors and the agent. And this layer should be automatically generated. And all of this, hopefully, should lead to a simplification of the verification of the agent decision-making process. Next slide, please. So the general idea of the framework, the starting point is the usual starting point we have whenever formal methods are involved, which are, we want to have the specification to model the several components, and we want to know what are the high-level properties of interest. Now, often we can start by looking at proper specification documents to understand what we want to model, but more often than not, we do have to talk with some system expert. And usually it's quite easy to come up with high-level property of interest. So for example, in this fake dialogue, which is partially fake, partially actually realistic, if we want to know what property of interest we want to check on some sensor S3, so the one that before was showing a drop from 49 to 32, the system expert should tell us in an easy way that if there is a drop, then the agent should reply. And we can easily write down this one as a high-level property. But then we want to know what sudden drop is. As Michael was mentioning before, natural language is one thing, being precise in specification is another. So we need to be quite specific, and we need to understand what sudden drop means until we reach the point of saying sudden drop means two consecutive values should not have a difference more than 4. Now, this kind of information is not high level, so this kind of information is quite precise, and that's why we include this one in what we call the background knowledge of the system. So after we have a list of high-level properties and a specification of the system. Next slide, please. We want to use those two elements to automatically generate a processing and verification layer. So the idea is that this layer will sit in between the sensors and the agent. And what this layer does, it intercepts the messages from the sensors, and we start checking properties. So for example, we wanted that all the values coming from S1 should be less than 20. So we will have some part of this processing and verification layer that will check whether or not the values are below 20, and will not return the values to the agent. We'll just say whether it's true or not that they are below 20. Similarly, we might have a component in this verification and processing layer that will check whether or not we have a sudden drop reported by S3. Now, the agent doesn't have to know exactly what the values are. We want the agents to focus on high-level topics. So the only things that the agent needs to know is that there is a property that says if you have a sudden drop, you have to replan. So the agents will just check what are the messages returned by this component checking for the sudden drop and say, okay, there is a problem, I'm going to replan. And this picture is, of course, an oversimplification of what's actually going on there. I will give a bit more details on this processing and verification layer afterwards, but the general idea is that there is not really a one-to-one match between one sensor, some component in this processing and verification layer, but the structure of this layer is a bit more complex. Next slide, please. So what is needed? The first things that we need, since we are formal people, are languages. So we have at least two languages. One formal language that is used for the high-level property specification. At the moment, we're using a metric temporal logic. And the idea is that this language doesn't need to work with the data coming from the sensors, but it still need to be able to express temporal patterns. For example, to be able to check whether a property is true or not within a specific time interval. We need also another language, which is the one that we use in the background knowledge, that is supposed to be some sort of bridge between the sensors data and the high-level language that is used for the properties. So this language is currently we're using a first-order metric temporal logic. It's supposed to be able to compute aggregation from the data coming from the sensors and to somehow translate the result of this aggregation into Boolean properties that can then be used to assign meaning to the more high-level properties. And this part of the languages is one of the challenges because, as usual, what we want is languages that are simple enough. We want to basically work with people that are not logicians, but the language should also be expressive enough to express the property of interest, and they are supposed to be practical. Now, there is the usual trade-off here is either you are incredibly practical and you are not expressive, or you are incredibly expressive and then you are not practical. The simplicity is a bit more subjective, but yeah, finding the right language is one of the challenges of the approach. Next slide, please. But there is an advantage of using formal languages is that we have access to formal technique. So we could use theorem provers and model checkers, and we could, for example, carry out some sanity checks on the specifications. An example, given the definition of sudden drop we had before, it should not be the case that sudden drop is always false or always true. So we are trying to model something where we expect the behavior of the system not to show sudden drop too often, but we still allow sudden drop to happen, and then we have the agent that will take care of the situation when this problem occurs. Next slide, please. What else is needed apart from languages? We want to automatically generate this processing and verification layer. And so the question is, how do we do this? What we do is we instantiate a hierarchy of runtime monitors. And this one is a hierarchy because there are different kinds of properties we want to check. Some of them are very simple, like something is less than 20. Some of them are more complex. They might involve temporal patterns. They might involve aggregation. And so we expect some monitor to use the outcome of some other monitor in order to establish the truthfulness of a property. And the hierarchy is obtained in a very simple way. It's basically just a parsing of the background knowledge and the set of properties we have. And to see that the hierarchy comes from them is relatively simple. We can have a property that is defined using another property that in turn is defined within the background knowledge. So just parsing this one will result in this hierarchy of monitors. But just to give an example of a very simple hierarchy, if we have a property like the values returned by S1 should not be higher than 20 for 5 minutes in a row. This means, for example, that we do allow, it's completely fine for S1 to give us values that are somehow higher than 20, as long as this does not happen for a prolonged period of time. And this can be basically dealt with two monitors, one that is simply checking whether the values returned by the sensors are less than 20 or not. And then another one that will take this information and create an aggregation to check whether these values are higher than 20 for too long. And the important point here is that the agent doesn't really care what are the values returned by the sensor, but the only things that the agent knows is that those values were too high for too long. And this part is basically taking care of all the processing and verification we want to have on the information streams. We are using runtime monitors that by default, by nature, what they do, they will verify that a particular property holds or not. Next slide, please. So as an example of a case study we are currently working on, we are working with colleagues from Orca. And as Rafael mentioned before, we have a colleague in our university, Matt Webster, that is working with a UAV system. And what they have there is they have a battery prognostic tool to estimate how the battery will change over time based on a set of actions that are supposed to be performed. And they, of course, have a sense of for the battery charge. And we start talking to them, asking what properties they might be interested in. And the high-level properties they gave us were, if the prognostic tool is too optimistic, then the agent should reevaluate the mission. Perhaps she will not be able to fulfill the mission, so might have to go back earlier. If the prognostic was too pessimistic, the agent should be able to schedule additional tasks. And if there is an abnormal discharge, then the agent should abort the mission. So these kind of properties are high-level properties we are more than happy to somehow formalize for the agent. But again, we need to be specific of what means for something to be too optimistic or too pessimistic, or what is an abnormal discharge. So we need to encode some information in the background knowledge. And the case of being too optimistic is something similar to the example that was in the previous slide. That basically means the difference between the expected value and the actual value is above a specific threshold, and this one is true for a time window. The reason why it's true, we are checking it for a time window and not just a difference on a single point, is because we can have spikes in the battery usage, and we don't want the system to say something is wrong just because there is a small spike. So we are checking on a time window to guarantee that actually the prognostic tool was too optimistic, and then the agent will reevaluate what you do. Pessimistic is basically a dual of this one. And abnormal discharge is the idea of, we know how much is the discharge rate if the system is running full power. If the discharge rate we are observing is worse than this one, then there might be a short circuit or the battery is just damaged and we need to abort the mission and substitute the battery, for example. So these are work in progress with the people from my colleagues from the Orca Hub. And last slide, please. And what we are currently working on is a prototype, because we are running some experiment with the battery example, but most of it is still hard coded. So we want to have this automatic generation of the processing and verification layer. Practical evaluation of the approach should follow, and at some point I should probably stop tweaking the language. I keep changing what is expressible and what is not expressible in the language, but that's my fault. There are still a lot of open questions. One of them is, of course, on the language, whether it's expressive enough or whether it's simple enough. But more interesting, the point is, are we adding too much delay by inserting this processing and verification layer in between the sensor and the agent? And how does this compare to a system that doesn't have this, but is the agent that is taking care of all the processing and verification? And that's the end of the presentation. Thank you.
Great, thanks for that, Fabio. I'm just gonna unshare my screen. Oh no, I'm not. I can see the chat. Here we go. So if anyone's got any questions, then please, oh, there's one in the chat already. Would you be able to tell how the time window or the threshold are defined?
So that's clearly system dependent. So that is something that the expert needs to tell us. So if they say the behavior should be observed in a time window of 5 minutes or 2 minutes, that's then something that is translating to the logic itself. But we do need an expert to tell us which one is the time frame that is supposed to be taken care of.
Okay, great. I had a question. I enjoyed your dialogue from the pedantic computer scientist and the system expert. Do you think that over time those sorts of conversations will get easier as people get used to working on these types of systems and it becomes a bit more normal, or?
I don't think it will become way easier. I mean, everybody has his own area of expertise, so we are not going to expect everybody to learn a formal language. So the discussion is will go on forever. It's just a matter of people will need to just get comfortable to it with the idea. You need to be really precise if you want to use formal language.
Okay, great. There's a couple more questions here. Oh, there's a question here to all the speakers. The approaches build on well-defined causalities and implications, some with exhaustive search for assurance. What about attaching probabilities and the statistical aspect to assess the probabilities of states, such as failures? Is this also part of your methods?
That's something that is widely studied in general. So the adding probabilities whenever uncertainty is part of the system behavior. So if clearly we cannot model the environment completely, and it's part of methodologies we use. So for example, the use of probability model checkers and so
on. Okay, and then do you have examples of more complex properties? For instance, a property where a value is high for some time and then low for some time?
Not at the moment. I mean, since it's a logical language, I'm happy to come up with any complex formula you want, but practically I don't have an example of such a property.
Okay, so this is, so this is related to the question about how you would know how the time window or thresholds are defined. Would you be able to tell who the expert in question is? How do you select the experts?
I would say it depends on the level of granularity of the property. So if it's a generic property on the system behavior, then someone that wants to use the system and expect a specific property to be true is the expert. If it's a property more on the hardware or software level, then the expert is probably a person that has built the particular piece of software or hardware.